Vanakkam, Namaste, Namaskar. We are discussing about the subject electromagnetic theory. So, in that, the third part we are discussing now, that is magnetostatics. So, magnetic field in a static one. So, today in this lecture, we are going to discuss about magnetic scalar and vector potential. Hi, I am Nageshwari, Assistant Professor, Department of EEE, RMK College of Engineering and Technology. Let me check the video. First, we are going to see about the magnetic scalar and vector potential. Here, actually, there are having two parts in this topic. You are having two parts. So, for the first part is scalar potential and second part is vector potential. So, we are going to see each and these two parts individually. Now, first we are going to see the scalar potential. So, before going to that scalar potential, so we need to give some introduction about this topic. Okay. So, let me check the introduction. So, in magnetic fields, actually, there are two types of potentials. So, the first one is nothing but the scalar magnetic potential denoted as Vm. I repeat, the scalar magnetic potential denoted as Vm. The second one is vector. So, the vector magnetic potential denoted as A, capital A. These are the two potentials in a magnetic field. To define scalar and vector magnetic potential, let us use two important vector identities. So, here the vector identities plays an important role to solve this problem, that is scalar and vector potential. What are the two identities? Let me check. The first one is nothing but the del cross del V is equal to 0. That is the first vector identity. So, I repeat, first identity is nothing but del cross del V is equal to 0, where V is nothing but the scalar. Now, the second one is nothing but the del dot del cross A is equal to 0. I repeat, del dot del cross A is equal to 0. Now, this A vector is nothing but the, one sec, yeah. So, now, this A vector is nothing but the vector quantity. Okay. So, these are the two vector identities we are going to use in this problem. Now, first, we are going to see about the scalar magnetic potential. First, we are going to see about the scalar magnetic potential. As I mentioned you, the notation for scalar potential, if Vm is the scalar magnetic potential, then it must satisfy the equation. So, what is that equation? Yes. So, del cross del Vm is equal to 0. This is one of the vector identity. So, it needs to satisfy this vector identity. Okay. So, now, but the scalar magnetic potential is related to the magnetic field intensity H. Of course, okay, you need to relate this equation with respect to H only. Okay, so therefore, we know very well H is equal to minus del into Vm. Okay, so we can correlate this equation in terms of electric field also. Okay, what is the relationship between, if you remember, there is a relationship between the electric field and the potential gradient. I repeat, I will recollect that once again. So, what is the relationship between electric field and potential gradient is nothing but E is equal to minus del V. Okay. So, we know that there is a relationship between E and gradient. Okay. So, the relationship is nothing but E is equal to minus del V. Okay, E is equal to minus del V. So, this is the relation between electric field and potential gradient. So, similarly, in magnetic field also, you have a relationship between the H and the V. Okay, so this is the relationship. What is the relationship? H is equal to minus del into Vm. Okay, so H is equal to minus del into Vm. So, what we can say, we can correlate this equation to the above equation. So, instead of del Vm, we can write it as minus H. So, therefore, we can say del cross minus H is equal to 0. That means, or we can say del cross H is equal to 0. So, but we know that there is one curl equation is nothing but del cross H is equal to J. Okay, del cross H is equal to J. This is nothing but curl J rule. Okay, so if you compare these two equations, that means del cross H is equal to 0 equation and the basic curl equation del cross H is equal to current density equation. Okay, if you compare these two equations, so we can conclude one important point, one beautiful important point, that is nothing but J is equal to 0. Okay, that is current density is equal to 0. So therefore, what we can say? So in scalar magnetic potential, so Vm can be defined for source free region where J, that is current density, is 0. I repeat, the scalar magnetic potential Vm can be defined for source free region. So where J is nothing but the current density is 0. So therefore H is equal to minus del Vm only for J is equal to 0. H is equal to minus del Vm only for J is equal to 0. So similar to I told you, no, there is a relationship between E is equal to minus del V. So similar to that, we expressed this equation in terms of the magnetic scalar potential. Okay. So therefore, so from this we can obtain as V is equal to minus integral of B to A H dot dl. So this also we can represent, okay, in terms of H. So now also we can correlate Poisson's and Laplace equation with scalar and vector potential. That is another beautiful important point in this derivation. Okay, in this derivation, so we are obtaining Laplace and Poisson's equation from these two potentials. So for, the first one we discussed scalar potential. No, okay, from the scalar potential we can obtain the Laplace equation. Okay, viewers, already you all know that what is Laplace equation. Laplace equation, the condition for Laplace equation is nothing but is nothing but del square V is equal to 0. Okay, so this is called as the Laplace equation, right? Okay, so therefore the scalar potential satisfies the Laplace equation. That only I am trying to say. How it is possible? Let me check. So it is known that integration of B dot ds is equal to 0. That is according to magnetic Gauss law. So we can say that integration of B dot ds is equal to 0. Now you apply the divergence theorem. You know what is divergence theorem? Surface integral is equal to the divergence of its volume, divergence of its volume of the vector, right? So therefore integration of B dot ds is equal to, so the volume integral of del dot B dv is equal to 0. So therefore, so according to this equation, we can conclude that del dot B is equal to 0. Okay, this is the divergence of Gauss magnetic law. Okay, divergence of Gauss magnetic law. So therefore, instead of B, okay, so instead of B, so we can write mu naught into H. We can write mu naught into H. So del dot mu naught into H is equal to 0, but mu naught is not equal to 0. Okay, so that you should remember. So del dot mu naught into H is equal to 0, but mu naught is not equal to 0. So therefore we can say, we can obtain as del dot H is equal to 0. Del dot H is equal to 0. Now also we know that what is H? You know what is H? In the previous exam, in the previous slide, we know that H is equal to what? Minus del Vm. Okay, H is equal to minus del Vm, right? Okay, you please remember that. So now you substitute that H in this equation. Now what is your answer? Del dot minus del Vm is equal to 0. What is del dot del? Is equal to del square. So del square Vm is equal to 0. For J is equal to 0. So this equation is closely related to what? This equation is closely related to Laplace Laplace equation. Okay, so this equation is closely related to what? Laplace equation. And also you know what is Laplace. Okay, what is Laplace? You know very well, the Laplace is nothing but what? Del square V is equal to 0. Okay, so we can say that so if you compare so these two equations, so we can conclude that from the scalar magnetic potential we can obtain the Laplace equation, and we can prove for Laplace equation also. Okay, so this is the Laplace equation for scalar magnetic potential. Okay, so this is similar to the Laplace equation for scalar electric potential also. Now what I discussed is, the first one is nothing but the magnetic scalar potential. So in magnetic scalar potential we got the expression as del square Vm is equal to 0, and now we are correlating this scalar potential with that of the Laplace equation. Also we know what is Laplace, like the condition for Laplace equation. So we obtained the Laplace equation from the scalar magnetic potential, and we are correlating that. Okay, so that is the first potential in magnetic field. Now the next one is nothing but so we are going to see about the second one, Vectormatic potential. The second one is nothing but Vectormatic potential. So in this Vectormatic potential, the second identity we are going to use. Okay, so the Vectormatic potential is denoted as A, that you know already, and is measured in Weber per meter. Okay, and is measured as like this. So we know that, so del second identity is nothing but del dot del cross A is equal to 0. Okay, so but according to what to say, point form, according to point form of magnetic field, point form are also called as a differential form. Okay, according to the point form of magnetic gas law, del dot B is equal to 0. Now if you compare these two equations, okay, so we can say let this be the first equation and let this be the second equation. Okay, let this be the second equation. Now if you compare these two expression, if you compare these two expressions, so what is your equation we can get? Yes, of course. So therefore we can obtain as B is equal to del cross A. Okay, so B is equal to del cross A we can obtain. Okay, so thus we can conclude that the curl of Vectormatic potential is nothing but the flux density. That means, so B is equal to del cross A. So this is an important, very important. So based on this equation the problems will come. It is a very important relationship. So you all must remember this equation. What is that equation? So del cross A is equal to B. So where A is called as the Vectormatic potential and B is called as the flux density. So this is one of the most important equation. Now, so also we know the curl rule. What is the curl rule? The curl rule is nothing but the del cross H is equal to J, right? Okay, so curl of H is equal to current density is another important relationship in a magnetic field. Okay, so what we need to do is we need to substitute this instead of H you can write B in terms of B. Okay, so H is equal to what? B by mu, right? Okay, so we can write B by mu naught. So del cross B by mu naught is equal to J. Now you can take this mu naught is that side. Okay, we can take this mu naught as that side. Okay, so if you take this mu naught as that side, then what is the answer? Del cross B is equal to mu naught into J. Del cross B is equal to mu naught into J. Okay, so also we know very well B. You know what is B? Okay, so what is B? Del cross A. So therefore we can replace this B to del cross A. So therefore del cross A is equal to mu naught into J. Okay, so del cross A is equal to mu naught into J. Okay, so using another vector identity, you know very well there is an important vector identity is there. What is that identity? Del cross A is equal to del of del dot A minus del square A. Okay, now what you need to do is let this be your third equation and let this be your fourth equation. Now you compare these two equations. Okay, now you compare these two equation. Okay, so if you compare these two equation, now what we can obtain? So we can obtain as, so del of del dot a minus del square a is equal to mu naught into j. Okay, so if you compare these two expression, so a beautiful relationship we will get del of del dot a minus del square a is equal to mu naught into j. Okay, so therefore, so from this what we can obtain? So what we can obtain from this? So from this we can obtain as, so j is equal to 1 by mu naught. Okay, so 1 by mu naught into del cross a is equal to 1 by mu naught into del of del dot a minus del square a. Okay, so these equation, okay, is equal to what? This equation is also equal to mu naught into j, right? Okay, so mu naught into j, right? So I can write it as like this. Okay, I can write it as like this. So j is equal to 1 by mu naught into del cross a, which is equal to 1 by mu naught into del of del dot a minus del square a. Okay, so thus if vectormatic potential is known, okay, then the current density can be obtained. If a is known, okay, so if a is known, so therefore we can obtain the current density. Now, so from the vectormatic potential we can obtain Poisson's equation. Okay, from scalar how we obtained Laplace. Likewise, so from vector potential we can obtain the Poisson's equation. How? Let me check. So Poisson's equation for magnetic field. How? For a vectormatic potential, we know just now only we have seen that del cross A is equal to B. Okay, so assume for steady DC del dot A is equal to 0. Now you assume that for steady DC del dot A is equal to 0. The divergence of vector is equal to 0. So therefore, you know the relationship. What is that relationship? So we know one identity, no? Vector identity. What is that identity? Del cross. Okay, so del cross A. So del cross A is equal to del of del dot A. Del of, so del dot A, del of del dot A minus del square A. Okay, minus del square A, right? Okay, this is according to vector identity. Okay, from this vector identity, so if del dot A is equal to 0, okay, if this is 0 means, then what is your answer? Minus del square A, va? So what is minus del square A? So minus del square A is equal to mu naught into j, no? That only we got, no? Mu naught into j. Okay, so that is why I have written as like this. Okay, minus del square A is equal to mu into j. So therefore I can write this del square in terms of Cartesian system. So what is Cartesian in terms of del square? You know what is Cartesian? Ax vector into del square into Ax. In terms of xyz I am mentioning the above equation. So ay vector del square ay plus az vector del square az is equal to minus mu into ax vector jx plus ay vector jy plus az vector into jz. So what I am doing is just I am writing this equation in terms of coordinate, in terms of Cartesian coordinates. Okay, that's it. So now what you need to do is you need to equate both the sides. If you equate both the sides, then what we can get? A beautiful expression we will get. What is that? Del square ax is equal to minus mu into jx. Del square ay is equal to minus mu into jy. Del square az is equal to minus mu into jz. Okay, so these three equations you will get. These three equations you will get. So therefore in general what we can write? So in general, so we can say del square A is equal to minus mu naught into J. Okay, this is called as what? Poisson's equation for magnetic field. So like in electric field, so we have obtained the Poisson's equation for magnetostatic fields. Okay, magnetostatic fields. This is a general equation for a Poisson's equation. So therefore, from the above equation, we can write as I repeat the same previous two equations once again in this slide in order to understand better. Okay, so in general we have obtained del square A is equal to minus mu naught into J. Okay, so this is the Poisson's equation for magnetostatic fields. So therefore from the above equation, so we can write as, how we can write, so we can write as Ax is equal to mu by 4 pi integration of, so Jx by R into dV, mu by 4 pi into Jx by R, that is Jy by R into dV. Sorry, it is a typing error. And Az is equal to mu. So this is nothing but this is nothing but y. Okay, this is nothing but y. It is not x. This is nothing but y. Okay, and also this is nothing but y. So Jy. Okay, and this is nothing but z. Okay, this is nothing but z. So this is nothing but z. Okay, so Ax is equal to mu by 4 pi into Jx by R into dV. Ay is equal to mu by 4 pi into integration of Jy by R into dV. Az is equal to mu by 4 pi integration of Jz by R into dV. So like that also we can write from the above equation. So in general, the magnetic vector potential can be expressed as A is equal to mu by 4 pi the volume integral of J by R into dV. So this is the Poisson's equation we have obtained from the magnetic vector potential. So I repeat that. So in this particular video we have gone through the derivation called as magnetic scalar and vector potential. So the first we have seen about the magnetic scalar potential. So from the magnetic scalar potential again we obtained a relationship called as the Laplace equation. Next we have seen about the vector potential. So from the vector potential, so we have obtained the Poisson's equation. So this is called as the derivation of the magnetic scalar and vector potential. So and also obtained Laplace and Poisson's equation. So thank you all. So thank you for watching this video.